Good afternoon, everyone. Thank you for joining us. We are recording today's webinar and we'll send it out to everyone along with the slides after this. If you have any questions, please put them in the chat box and we will answer those at the end. I'd like to introduce our speaker today, Marv Kaiser. He's the Global Electrochemistry Environmental Product Manager. He graduated from the University of Illinois with a BS degree in analytical chemistry. He has spent much of his career training, marketing, sourcing, selling, and managing electrochemistry and spectroscopy product portfolios. Marv is an experienced speaker and has presented at numerous conferences, including PittCon, WEFTEC, and AWWA. Take it away, Marv.
Thank you very much. Good afternoon, and thank you for attending today's Midland Scientific webinar. In today's webinar, I'd like to discuss some common drinking water test methods with a specific emphasis on turbidity and chlorine colorimeter. So first, I'd like to discuss the three main components of water quality testing. Those being sample collection, the actual physical testing, and then specific sample analysis, whether it's metal analysis or organic analysis for pesticides. Those are three of the main components to common drinking water tests. So sample collection sometimes gets overlooked, but is a critical part of water quality testing. Chain of custody and storage requirements are key. Storage at a specific pH and temperature in a contaminant-free plastic bottle, for example, are key requirements to many of the tests. As far as physical testing, there's a lot of different accepted methods. For example, some parameters will have multiple accepted test methods. Fluoride, nitrate, ammonia, potassium, sodium, hardness, for example, have an ion-specific electrode method and a colorimetric method that are both accepted. Chlorine, alkalinity, hardness, iron testing, those also have multiple accepted methods, for example. Those would be colorimetric as well as titration. So I first wanted to give you a little insight into Environmental Express and who are we? Environmental Express is a product company. We have extensive portfolios in water quality testing, air sampling and testing, and soil testing. Specifically for the electrochemistry portfolio, we have an extensive portfolio including testers, portables, benchtops, calibration solutions, and electrodes. We have three manufacturing facilities, one in South Carolina, one in Florida, and one in Texas. So first, let's dive into turbidity, what it is, some of the best practices, the treatment process for a typical water treatment plant. I wanted to give everyone a better understanding of that process and explained where the different instruments or test methods are used. So turbidity describes the amount of light scattered or blocked by suspended particles in the water sample. Clear water has low turbidity. High turbidity water is cloudy or murky. Turbidity is caused by particulates of soil, organic matter, metal oxidation, or similarly matter suspended particles in the water sample. An epherometric meter is a particular type of turbidity meter that measures the amount of refracted light detected at a 90-degree angle from a culminated tungsten light source. It is the specific design mandated by the EPA method 180.1 for drinking water standards regarding a post-filtration turbidity monitoring compliance in water treatment plants. In practice, it's also used to indicate the potential presence of sediments, algae, microscopic pathogens such as Giardia or Cryptosporidium in the water sample in relatively low particulate levels. Turbidity is measured in NTUs, nepherometric turbidity units, and FMUs, which is formazine nepherometric units. Ultimately, turbidity measurements are an important part of water quality in water treatment plants. They help the operator achieve the most important goal, making water safe for consumers to drink. So I wanted to do, as I mentioned, a quick overview of a treatment process, starting with the turbidity design, the 181.1 method, using a tungsten white light source is a great choice for evaluating surface waters entering a water treatment plant's application or facility. It can identify deteriorating inflow conditions in time to adjust flocculation or coagulation treatments to improve the chances of meeting post-filtration turbidity compliance requirements. So two of the coagulants, and you'll often hear them intermixed as coagulants or flocculants. These are both the same type of compounds. I consider coagulants specifically to be inorganic salts, such as the ammonia, aluminum-based coagulants, such as aluminum chloride and aluminum sulfate. There are also iron-based coagulants. The two most common are ferric chloride and ferric sulfate. These chemicals are used to neutralize the charge and colloidal impurities and enhance the coagulation of suspended solids across a range of municipal applications involving raw water treatment, wastewater treatment, and effluent treatment. They are widely used to reduce organic matter, color, turbidity, and microorganism levels. I also wanted to point out the graphic on the left side of this slide, and specifically to compare a no coagulant treatment water flow versus a flow that has a coagulant added. Initially, you'll see a small spike in the NTU value, the turbidity value, and then as the floc or colloids begin to form in a clarifying tank and settle to the bottom of that tank, the NTU level will be decreased dramatically. So this slide is specifically a simple potable water treatment process, and it's important in my mind to explain this process so there's a better understanding of turbidity itself, where it's used, and why it's important. So at the headworks of a plant, they will normally measure pH and flow and turbidity. pH, obviously, so they can determine if there's a chemical slug coming into the plant. Flow is critical as well. Each water treatment plant has a basic maximum flow rate in millions of gallons per day. Obviously, if that flow rate is exceeded, it creates all kinds of problems within the plant itself. But in this example, we want to talk about turbidity prior to coagulation or flocculation, and the addition, for example, of ferric chloride in this process is injected into the water flow. That dissolves, and as that flow enters the clarifier, the flocs or colloids begin to form at the surface. As they get larger and heavier and larger, heavier by space, they begin to settle out and slowly float to the bottom of the clarifier. Now, these clarifiers are normally a cone-shaped in design and will have a valve and a pump at the base so that they can remove the sludge. once it hits a certain level in the tank. But the turbidity measurement here, after a coagulation or floc addition, is a key to determining settling rates and optimizing the amount of coagulant or flocculant that's being injected into the water. After settling, the water is then additional conditioning can be performed if they're removing nitrates, phosphates, other type of impurities. Then the water would flow into a filter bed. The filter bed is made of coarse gravel, fine gravel, sand, and the most important component, activated carbon. The activated carbon does a great job in reducing fines or small sediment particles. Some ionic species are removed as well. Once it passes through the filtration bed, you want to have a level of 1 NTU down to about 0.5 NTUs. That is fairly clear water, and it won't interfere with the disinfection process. The disinfection process is next, specifically the addition of an oxidizing agent, which we'll talk a little bit more in the presentation, but for now, it's specifically added to remove and kill any bacterial or viral contaminants. The water is then pumped into a storage system or directly out into a distribution network. So a couple things here are key, that the measurement of turbidity prior to the clarifier and then after the clarifier and filter bed process allows the operator a chance to determine settling rates and understand how well both of those pieces of equipment are functioning. Pardon me. Some of the turbimeter applications would include EPA and ISO compliant turbidity measurement, potable water testing. The EPA has mandated that the turbidity of the drinking water must be measured every 15 minutes and recorded for reporting. Filter beds, I didn't talk much about backflush testing, but specifically, once the filter bed runs a specific amount of time determined by the operator, it can be a month, it can be 3 months, it could be 6 months. They need to be backflushed. The entire filter bed is backflushed, and then the water is pumped off, refreshing that filter bed so that it can continue to filter out fines and other specific impurities. Breakthrough events are when the water creates a path through the filter bed and the water is not evenly distributed across the filter bed. So a breakthrough event is also very costly if it happens prematurely and needs to have action by the operator. Monitoring the quality of water in rivers and streams, measuring the turbidity of wastewater effluent to monitor for the presence of harmful pathogens. Another application, as I mentioned, was for municipal water and wastewater plants, clarifiers for optimizing those settling rates. Clarifiers are a key piece of equipment in a drinking water plant as well as a wastewater plant. Another specific application is for boiler water testing. Boiler water is a pressurized closed system that its biggest enemy would be oxidation or rust. So you want to make sure that the water in the boiler contains no rust. Another application is food and beverage, processed water testing. This is the incoming water that the company will use to produce their product. Semiconductor, also very high water purity and clarity is required. And then typical chemical applications where the company wants to look at the appearance or clarity of their finished product. So next, I wanted to talk a little bit about water quality standards having to do with turbidity. Uh, to further complicate turbidity measurements, there are several water quality standard methods and design standards in use. The US EPA has approved 8 methods for monitoring drinking water. Until 2009, only 4 methods were approved. Uh, the key method for us is the US EPA method 180.1. This is using a white light tungsten filament light source in your turbidimeter. The second is standard method 2130B. This is nearly identical to method 180.1, but it uses the FNU units versus the NTU units used in the method 180.1. Third method is the GLI2. This is the first instance of LEDs being used in a turbidimeter sensor. We'll talk a little bit more about that. And then finally, the Hach method 10133. This is the red light laser method with the light energy output from 630 to 690 nanometers. In 2009, 4 additional methods were added to the list. And the reason I mention these is just so that we understand that there's a lot of different methods out there. We'll focus in on a couple specifically, but just to build awareness here. Mitchell methods, M5271, which is also a laser method, M5331, which is an LED method in the 510 to 540 nanometer range. That's the in the true white light range. The Orion AQ4500, this is an expanded spectrum LED application using both a white light LED and a infrared LED. And then finally, the AMI Turbidowell. This is a non-contact method, fairly new. It's a process instrument specifically. Of all of these methods, obviously the EPA method 180.1 and the ISO method 7027 are the most well-known guidelines and are internationally recognized when verifying turbidity meters and turbidity sensors, their performance, and their method compliance. Outside the US, for example, the ISO 7027 method using an 860 nanometer LED light source is the quality standard. The monochromatic light source, the ISO 7020, eliminates most color interferences, does really well with higher concentration from the range of 830 to 890 nanometers. So essentially and you'll sometimes hear the 860 nanometer LED light source referred to as an infrared light source. That's because that band happens to land in the infrared section of the electromagnetic spectrum. With regulatory compliance important in the municipal water drinking application and water treatment plants specifically, measuring turbidity can also help keep costs down. As I mentioned, clarifier settling rate optimization is key, as well as filter bed, backflushing, and monitoring for breakthroughs within that system. Taking regular turbidity instruments can optimize your bed performance by establishing efficient filter backwash cycles. So they know approximately when that filter bed needs to be backflushed and regenerated, so to speak. And in the case of filter breakthrough, turbidity readings can indicate the breach of the particles before it becomes a really costly problem, and they need to shut down that filter bed and essentially rebuild it. So next, I want to talk a little bit about light sources. Light sources are key in the evolution of turbidimeters. one of the most important advancements in the accuracy of turbidity measurement since the publication of the original EPA method 180.1, relates to ratio instruments and light sources. So I want to talk about some of the newer instrumentation and the improved accuracy and repeatability. Turbidity can be particles in water consisting of finely dissolved solids, divided solids, or fines, larger than molecules, but not visible by the naked eye. These range in size from 0.001 to 0.15 millimeters or 1 to 150 micron. Now, the white light turbidimeters measure the particle scattering of light from a tungsten light source and the wavelength of the spectral peak response of the detection system should be between 400 and 600 nanometers. The white light, a tungsten filament white light source, accomplishes that. The one Mitchell LED simulates that as well. For LED or infrared turbidimeters, a wavelength of 860 nanometers is the optical LED wavelength for measurement of low turbidity values. So today, the LED and laser diode light sources are capable of providing better performance, all at the low end, under 5 NTUs, and have been approved as acceptable alternatives to the original tungsten light source as specified in the original method 180.1. In fact, they provide a stable, more controllable light that avoids the changes in power and geometry experienced with the tungsten bulbs over the life of their operation. So essentially, there's a couple of downfalls with the original white light tungsten element light source. Specifically, they heat up, so they don't last quite as long as the LED. The LED does not heat up quite as much. The other problem that can arise is differences in light intensity. If the voltage supply to that white light source is consistent and non-fluctuating, it's a pretty stable light source. But if there are fluctuations in the voltage to the light source, that can have an increase in light intensity as well as decrease. The result is a wide and accurate measurement range from 0 to 1,000 NTUs with readable resolutions between 0.01, 0.1, and 1 NTU. And that's range specific. One of the tricks in getting the instruments to be as accurate and repeatable as possible is to break that 0 to 1,000 range into multiple smaller range. So these precise readings are matched with repeatability and accuracy under 1% or 0.02 NTUs. Units. So for a Formazin nepherometric unit, the FNU, that is similar to the nepherometric turbidity unit, the NTU, in that both measure scattered light at 90 degrees from the incident light beam. Now, the FMU units is equivalent to the NTU unit and is measured normally with an LED of the infrared light source according to the ISO 7027 method, whereas the NTUs are used with a white light source, such as method 180.1. Next, I'd like to talk quickly about well, I'll make one final statement about the enhanced performance and possible by these light sources has led to an immense improvement in stability, accuracy, and repeatability of the turbidimeter readings. The instrumentation with built-in software that complements quality assurance and quality control requirements can improve the operating integrity and boost the end user confidence in the turbidimeter readings. In water treatment plants, multiple turbidimeters or standardizing on one specific method or type of unit is commonplace, and maintenance, calibration, validation requirements uh, are all made much easier if they standardize on one type of equipment. So next, I wanted to talk about calibration standards, specifically the two EPA compliance standards. Uh, First one we'll talk about is the AMCO Clear standard. This is a primary calibration standard. It's good for online, lab, or portable instruments. It is non-toxic. You can essentially pour this down the drain when you're done using it. It's stable. It is compliant to NPDES and NPDWR regulations. It is a copolymer, essentially copolymer beads that are in suspension in this liquid. Very uniform, very stable. They don't settle out of solution. I would still recommend taking the cuvette by the top, place your thumb at the bottom. You don't want to get any fingerprints on the optical path, but inverting any turbidity standard just to make sure that it is consistent and well mixed. It's homogeneous. Do not get fingerprints on that glass cuvette, as that'll definitely mess up your readings. The second standard we want to talk about is also a primary standard. It is formazine. This is specifically a stabilized formazine. Now, this does have the tendency to settle out of solution, so you are asked to invert and mix this standard back up before each use. Again, this is just minor agitation, inverting the vial back and forth. You do not want to create bubbles. Bubbles are not good in turbidity measurements. So normally for a white light turbidimeter, I would recommend daily or every other day calibration checks, just due to the light variations and light intensity variations that are possible with a white light source. So let's talk for a moment about calibration and verification frequency. As I mentioned with the white light tungsten source, I like to do it more frequently. Calibration at least every 90 days and verification at least once a week are required by rule. Again, if you're using the older tungsten light source, I recommend more frequent validation. To be considered an acceptable verification, turbidity measurements greater than 0.5 NTUs must be within 10%, which equates to 0.05 NTU of the reading assigned to the standard or reference material in use. The temperature measurement for electrical calibration is typically 73 degrees Fahrenheit or 23 degrees Celsius. Very cold samples can result in condensation forming on the glass cuvette. And this is especially true with the white light tungsten light source, as I mentioned. You won't see this as much with the LED because they don't produce nearly the same amount of heat. Now, normally with water treatment plants, the temperature of the incoming flow is very stable, changing, a half a degree or a degree over a month's time. So it's usually not a condition. I just like to point out that be careful with very cold water samples when using a white light tungsten light source. So let's talk about best practices quickly. The include low light stray light instruments. That's a key. Most instruments nowadays are very low stray light. They use a black optical path to absorb any stray light internally, and are sealed significantly that the stray light numbers are very low. Clean, scratch-free cuvettes is another key requirement. No gas bubbles, as I mentioned. Indexing the cell. On each of our cuvettes, you'll find a small triangle. You match that triangle up with the triangle on the instrument itself. That is supposed to be the best optical path through that glass cell. And good calibration techniques. Again, no fingerprints on the cuvettes, a well-mixed calibration standard, and scratch-free cuvettes. I always recommend our customers keep a package of spare cuvettes on hand. Some folks like to use the silicone oil, for example. That fills the impurities in a glass cuvette. But it's been my experience that that silicone oil, if it's not properly wiped off, can also collect dust and other fines that might be floating in the air. So keeping the glass cuvettes clean and scratch-free is a key to good accuracy and repeatability. The maximum level of turbidity of the CFE must not exceed 1 NTU for membrane filtration and 5 NTU for gravity filtration. Turbidity should ideally be kept below 1 NTU because of the recorded impacts on disinfection. As I mentioned, typically a water treatment plant will have a 0.5 to 1 NTU outflow, and that's achievable in most well-run plants and doesn't cause any interference in the disinfection process. All right, so I wanted to take a quick view of workflow of turbidimeters, specifically shamelessly plug our products. Our T100 white light, we offer this instrument in a kit format. This is the standard tungsten white light source. We also offer this with the LED light source as well. This specific model has data logging up to 200 data points, includes a flash drive with the software, and it can be easily downloaded onto an Excel file. Our T80 turbidity meter kit, this does not offer the data logging option. This is more of a quick check type instrument. We do offer this in the white light version and the LED or infrared version as well. Again, I can't stress enough, have replacement sample cuvettes on hand. Scratches and fingerprints are enemies of sound turbidity measurements. Primary calibration kits are offered as well, both for the T100 and the T80 instruments. And we do have separate calibration sets for the white light source compliant with method 180.1 and the infrared method, which is the ISO 7027. So now I'd like to move on to disinfection, another obviously very important process in a water treatment plant. Disinfectants, these are chemicals that are added to the water and wastewater systems to dispose or kill of unwanted microorganisms. There are various disinfectants and biocidal products available, some of which have a wide range of effects and killing several kinds of bacteria and viruses. The key here is that you want to use a fairly strong oxidizer, like a sodium hypochlorite or a calcium hypochlorite. This will kill the bacterial and viral components. These act as oxidizing the cell membranes of microorganisms, causing a loss of structure and leading to cell lysis and the death of the cell. Some of the most popular chemicals are, as I mentioned, the hypochlorites, ozone, chlorine dioxide. Potassium permanganate isn't used as much anymore, and fortunately, neither is chlorine gas. If you've ever been to a plant, you see the large green tank. That's a chlorine tank, and those are quite dangerous. The EPA compliant reagent for the colorimeter is called DPD. This is approved for reporting methods, reporting concentration of free chlorine or total chlorine in your water. The method of measuring chlorine residual in water, as you see on the right side of this slide, is our colorimeter kit. Has the colorimeter, has 100 of the free chlorine foil pouches or unit doses, and 100 of the total chlorines included. The glass cuvettes and the plastic cuvettes are used for the high range. This residual may be determined by using either titration method or the colorimetric method we just mentioned. And DPD stands for N,N-diethyl paraphenylene diamine. Some of the applications for chlorine colorimeters, and these are EPA as well as ISO compliant. Potable water testing, mandated by the EPA at 1 ppm or less for drinking water. And again, the reason they disinfect is to kill the bacterial and viral components, but you also want to maintain a free chlorine residual in your storage tank or your distribution network. This is the most widely used disinfectant in the world. It's suitable for a wide variety of applications and industries. Anyone using chlorine as part of their treatment process needs to monitor the concentration of chlorine. Measuring free chlorine in the wastewater effluent ensures that the aquatic life downstream from wherever the plant is releasing its water won't be harmed. Most chlorine tests require the use of DPD. Again, this is EPA compliant to method 4500G in standard methods. The DPD reacts with chlorine in the water sample to form a Worcester dye and an imine as their end products. So to summarize some of the key applications, again, the municipal drinking water plants, as I mentioned, chlorines is added to remove the harmful pathogens and to keep a residual in the distribution channel. For municipal wastewater plants, chlorine is added at the end of the process to kill any bacterial or viral contaminants that have made it through the treatment process. And the free chlorine must be removed before the effluent is released. Another key application is for food and beverages. Specifically, I've helped multiple customers with sanitizing baths. So these folks are essentially washing fruits or vegetable in a 10 to 20 part per million chlorine bath. And of course, they're thoroughly rinsed and cleaned after that. But again, this kills E. coli, any of the other deadly coliforms that might stick to the vegetables or fruits. And again, this goes through a very vigorous rinse cycle and soak so that there is no chlorine residual left on the fruit or the vegetables. Last application is cooling towers. Chlorine is used to control bacterial growth in a system, including Legionella, which is fairly serious. Now, our chlorine workflow, our 200 Model 200 chlorine colorimeter, the DPD powder pillows or unit doses for testing for free. There's a separate powder pillow for testing for total chlorine. Primary chlorine standard kits. Now, many regulators or auditors require this to be done, some every month, some every quarter, some once a year. But it's important, I believe, that we have the capability to calibrate the instrument to a primary standard. The Secondary standards are also available. Now, these are key. This is what you're going to use every day to validate the functioning of the instrument, the correct functioning of the instrument. This would normally include a 0.0, a 0.02 ppm, and a 2 ppm. And then also the replacement cuvettes for the colorimeter itself. Finally, just a quick comparison to show how our colorimeter should do in the marketplace. Specifically, I compared it to the market leader. These are both compliant to standard methods 4500-G, have an LED light source, silicon photodiode detector. The range is 0.02 to 8 parts per million for both free and total chlorine. The accuracy is where I'd like to point your attention. Our instrument is plus or minus 1 nanometer. Theirs is plus or minus 2. Our full-scale photometric accuracy is rated at 3%. They will not publish what theirs is. 16 data sets with time and date stamp versus 50 on their instrument. And then finally, the price. Our instrument comes in a kit format, includes the instrument, the cuvettes, the powder pillows. Their instrument is sold singly. You have to purchase the reagents separately. And then finally, summary is better price point, better power performance, primary and secondary calibration, and a better warranty. We have a 2-year warranty versus their 1-year warranty, and a better price point in the kit format by 20%. That ends my presentation for today. Any questions?
Thank you for the presentation. That was a lot of good information. If anyone has any questions, you can go ahead and put those in the chat box. I don't see any right now. Again, we'll also be sending out the presentation along with the recording, so you can refer back to that. And if you have any other questions, you can send that our way. Okay, thanks everyone for the time today. We'll give you some time back. Thank you.